All right. Let's look at the bottom-up tabulation technique for the knapsack problem. We just solved to show the top-down memorization technique. So now let's look into this one, the bottom-up tabulation technique. So in the above approach, right, the top-down one, memorization one, we need to first check whether a problem has been solved before solving it, and it adds extra overhead and slows down the algorithm. By nature, a recursive algorithm uses space on the call stack, and we can overcome both of these problems using tabulation, which is an iterative, bottom-up dynamic programming approach in which we first solve the smallest subproblems and then combine their solutions to solve larger subproblems till we have solved the overall problem. Okay. So what issue are they complaining about here? Let's look at the code very quickly. So the fact is, whenever you call this function recursively, you end up like adding another entry in the call stack. And even if it's already there, right, this like adds some space overhead, space and time overhead. So instead of doing that, we are gonna use iteration. So we're not going to use a recursive approach. We're going to use an iterative approach. And in general, every recursive algorithm has an iterative counterpart, right? Always remember that. And we're going to look at the iterative counterpart of this problem now. So we need to set up a 2D table, dp, of size n plus 1 and capacity and by capacity plus 1. And each row corresponds to an item, and each column corresponds to the remaining capacity of the knapsack at any point. There's a very useful image that we're going to show in a few, but we're going to have to endure just reading through this first. But the image is going to make everything a lot clearer. So therefore, the dp at ij stores the value of the combination such that at any I and any j, the combination consists of one or more of the first I items, and its weight does not exceed j. Okay, and again, this diagram is going to make all this a lot clearer, so just bear with me for a second. There is no combination of these items that yields a higher value. Okay, so and this is how the algorithm works. Similar in some ways to the recursive one. So first we have the first column is 0. Since the value of the knapsack is 0 when the capacity is 0, so I mean, if the capacity is 0, you can't put anything in there, so the value has to be 0. We fill the first row with 0 to represent the base case where none of. So we're going to fill all the first column, right, with 0, right? And then we're going to also fill the first row with 0 to represent the base case where none of these items has been added to the knapsack. Now for the remaining rows and columns, we iterate through them from the top left to the bottom right. For each entry in the table, we check if the weight of the current item is less than, just like the recursive one. We check if the weight of the current item is less than or equal to the current available capacity. Sorry, I'm so sorry for this block of text, but just bear with me. So we're going to check if the weight is less than or equal to the current available capacity for each entry. Okay, the weight of the current item is less, and if it's less, so it can fit in the backpack, we have two options: either to include it or to exclude it. So because it can fit doesn't mean we're going to put it in there. It depends on we're trying to maximize value here. So to include the item, we first make space for it. And how do we make space for it? We subtract the weight of the item from the current capacity to get the remaining capacity of the knapsack. And now to find the highest value combination of items for the remaining capacity, we should have gone through it by this point, and we look up the solution to this subproblem from the DP table, the dynamic programming table. And here's a concrete example that to me wasn't super concrete, and so I'm gonna just skip it. Right, I'm just gonna skip this. You can read it if you want, but it didn't really explain it for me best. But this diagram was kind of useful. So let's look at it. So below, this is a representation of the knapsack showing the current item included. So the current item is this, right? But then we get the best combination, right? Whatever we're gonna update in our table, our 2x2 and our two-dimensional table, is going to be the current item and its value, right? Its weight and its value, plus whatever is the best combination of items without that current item. Like the remaining space, right? The remaining space that current item affords, right? What's the best thing that remaining space can take? And now the total value of the knapsack is that the current item plus the value of the best combinations that fit, okay, in the capacity minus the weight of that current item. And so that's our first option, right? Is to include it. And then our second option is to exclude it. And we just, to exclude it, we just look up the value of the knapsack at the current capacity from the previous row of the DP table. And this is the highest possible value obtained at the current capacity without considering the current item. The highest possible value obtained at the current capacity without considering the current item. So we choose the option that yields the maximum value and update dp for at ij accordingly. Now, in general, the rule to update the cell in row I and column J may be coded as follows. This is super important. So at any I and J, we check which is bigger, whether we include the value, which is what this represents, right? Whether we include the value is the current value plus the value without the weight, right? The optimal value without the weight, or without that particular item at the current capacity. So in the previous row. That's what all that block of text we just spoke about is expressed in this equation, and we're going to see this often, so I can move on for now. Otherwise, so in the case where the weight of the current item is bigger than the current capacity, we can't include it in the knapsack, so we just reuse the solution to the sub problem. So at the previous, you notice that's the same thing here, right? dp at I minus 1 and just j. That's the maximum value that can be obtained at the current capacity without the current item. So repeat the steps above till all entries of the DP table have been filled, and we'll return the last entry, which contains the maximum profit for the given capacity. Now this slide is gonna tell us the whole story. Okay, and we'll move through the slide and the code, so bear with me. Stay tuned. So this diagram explains the entire wall of text that we just endured for the past, 5 minutes. And you can see that we created a table, a two-dimensional array. The columns represent the capacity, right? In this case, our example, the capacity is up to 6. So this is a concrete example that I feel is more useful than the one I skipped earlier. And then each row represents a particular evaluating the particular items from 0, from evaluating no item in the knapsack, to the first, the second, the third, and the fourth item that you can see here, right, with the corresponding weights and values. And just this setup, I think, is worth showing in the code. So this is the former solution, right, the dynamic programming solution. You can see how long it is, right? And then this is our iterative solution. So compare yourself. How do I do this? Actually, no. So this is the memoized solution, if you remember, super long. And this is the iterative solution. And now I want to show the setup. So we have this function, this single function, and we're not that doesn't call itself. We pass in the capacity, the weights, and the values. So these things. So the weight, the values, the array of values, the array of weights, and with the capacity, which is a number. In this case, 6 is the number. And so we get n, which is the weights dot lengths, and we create this two-dimensional array this way. So a new array, fill it with a bunch of zeros, then map for each entry in the array. We create, for each row, we create a 6 indexed, a row with 6 spaces, right? Another like array, 1D array with 6 spaces and add zeros to it. So everything is gonna have 0, right? And everything is filled with 0. Well, in this case, this diagram is not 1-for-1, because what we just, the code we just showed, every single thing here is 0, starts out at 0. However, here the reason we're gonna keep these ones 0 is because for the base case, we make the first row equal to 0, representing the value of the knapsack when no item is added to it, right? So for the column, right, the base case, first column is 0, because since the knapsack cannot have a value greater than 0 when its capacity is 0, because it can't hold anything. So it's just 0 here. And then in this case, we're not evaluating any item. So no matter how big the back is, if there's no item to put inside, its value is going to be 0. So that's what that looks like. Now we move on. So we have a nested loop here. We're looping from 1, from the value for evaluating the first item that we can add, like in the array, which is this one, right? This item index is 0. And for the capacity, right, the first capacity from 1 as well. So far as less than the capacity, so far as less than the number of items, right, number of weights. You can see that. Then we do the thing, right, where we evaluate, can the current thing fit into the bag? or can it not? And now we do different things accordingly. Now remember this formula that I said is important, right? It's here, it is. And I feel color coding here is super useful. So here we're evaluating I1 and J of 1. And now the weight of this item is equal to the current knapsack capacity, because the current knapsack can hold one thing in this sub-problem. Therefore, we take the maximum value of the two options, including this item in the knapsack or excluding it. And this is what that looks like in code. The maximum value of including it is, that's what this line is, and then excluding it, that's what this line is. And pay attention to the color coding, because blue is for including, right? So the maximum value of including it from here to here, and then excluding it from, that's this thing right there. So the first value, that's the first item, right? So subtract 1 from it to get it from this array, because 1 is the second item, if you can see. So it's 1 minus, is minus 1, whatever n is, we say minus 1 to get the actual value there. And the weight that's left, so equals attention. I minus 1, that's 1 minus 1 is 0. So it's dp of 0 at I of 0 up here. And the weight, so the weight is 1 here. So in this case, we are evaluating a situation where we only put this one item in the bag, and the bag can only hold something of weight 1. So if we do that, right, we're going to have 1, including it, that one thing, plus nothing else, because there's no space for anything else, right, if we include it at this point, right, of the size of the bag. But we're increasing the size of the bag systematically and increasing the number of items we're evaluating at each size systematically. So it's going to look like this. Yeah, you can pause this and look at it, but this is pretty much the whole procedure for this algorithm, and we're at the home stretch. And we do that, and then this is evaluating it if we don't add this first item into it. And what do we do there? We already know, okay, if we're not evaluating no item, right, that is this one, we already know everything there is 0, right? Because if there's no item to evaluate, no matter how big the bag is, right, this is gonna give you 0. And in this case, even if the bag can hold one thing, if there's nothing to add to that bag that can hold one thing, then its value, its optimal value is nothing, it's 0. So it comes down to this, right? And they do it step by step, which is so useful. And equals this, right? Evaluates to that, and then evaluates to the maximum value between 1 and 0, which turns out to 1. So in this case, including the item, gives a bigger value than having no items at all. That's for a bag size of 1, where we're imagining where we only had this item to consider. So now we fill the rest of the row 1s for 2 reasons, right? Now the code is going to actually go through it and fill it for us. But just visually, we know that everything else has to be 1, because there's only one item to evaluate, right? And if at the size of 1, the best thing to do was to include that one item, then for 2s, they're going to be the same thing, because there's no other item to evaluate. We're imagining the rest of these don't exist pretty much at this point. And so everything else is going to be 1. Okay. Now, we've solved all sub-problems. I remember in dynamic programming problems, the sub-problems add up to give you the optimal solution for the bigger problem. And so we solved the sub-problems for all 6 capacities while only considering item 1, like the first item. And item 1 is the item indexed at 0, right? So standard programming. So now we do the I of 2 and J of 1. Meanwhile, right, everything we just did is expressed in this, is found in this expression, right? This is the same computation, right? The item, if we include it, right, that's what this is, right? And the item, if we exclude it, that's what this is, okay? Now, now in this case, right, now we're still at the first capacity of 1, but we're considering the second item over here. Now this second item is on its own bigger than capacity of 2. It's larger, and so we can't include it in the knapsack. It doesn't fit. So the value from the previous row is reused. And what does that value represent? It represents the best combination of items found before this second item was considered for this capacity. And that just turns out to be, oh, what was the previous row? At that same column with the value at the previous row, let's just copy that over. like so, and we set it to be what it is. Now, when we move on, when we increase the size of the bag theoretically to 2, now all of a sudden this thing can fit in because it weighs 2, and now we're at capacity 2. So what do? We check, okay, how is it going to work if we include it? And by the way, that's the else statement here. Well, what we just considered is the else statement here, right? If it doesn't fit, right? If the current item doesn't fit in the bag for the current capacity, right? Just get what was the previous best value for that capacity, assuming that we don't add that current item. So that's what that is, that else statement. And that's the whole thing. That's the whole process. There's nothing else, as you can see, right? There's nothing else in here, right? We just populate that table, then return the very last thing, and we're done. But let's step through it a few more times. We're probably not going to do it 20 times. But so for I of 2, so we're considering these 2 items, right? The first 2 items. And we have a hypothetical size of the bag that is 2. So, but we're acting like these last 2 items don't exist for now. And it comes down to that same equation, right? The value, the current value plus the value, what it would be if that thing is already in the bag. So the including, right? Basically, what's optimal if what are we going to get if we include it? What are we going to get if we exclude it? Which one is better, right? If we include this item, right, the second item in our equation right now, if we put it in the bag, what are we going to get? If we don't put it in the bag, what are we going to get? So in this case, including it works, and we can see the computation here. Oh wow, this video is 16 minutes long already. So many words. So many words. Let's wrap things up, okay? I don't want a 20-minute video. I'm done with those. So yeah, just pay attention to that. And if we add it, yeah, the value at 1, right? That's this guy, right? The value here, 5. Plus, okay, if we've included it, that means, oh look, its capacity is 2. We're evaluating capacity of 2. There's no space for anything else. And that works out, right? And that works out because when we do this math, we see that we have the value at dp row 1, yeah, index capacity of 0, because there's no space, right? Once we've added this 2, there's no space. So, and it works out. This equation helps us work that out. And that's if we include it. But if we exclude it though, right, we're just gonna pick 1, the 1 right up here, same capacity but just without the item, and that's what we get. So in this case, it's better for us to include it, and that's what we end up with. And that is literally what we just keep doing till we get to the end, right? And then in this case, for 4, 5, 6, we only have these 2 items to add, right? And basically adding them is what we're gonna do. That's the best combination we can have for the remaining hypothetical capacities, right? Because we have nothing else to add to modify this, right, or exclude. So that's what we have. That's what we have to work with. So that is the whole procedure, and we just keep doing that. We just keep going. We just keep going. Sometimes we exclude because that's what's best. Sometimes we include because that's what's best. All the way to the end. And then at the end of the day, we just pick the last thing and send it out. Okay, so that's all there is to this problem. Now, one simple optimization I think is worth mentioning, and I'll mention this one. There's another one. There's another optimization, but this one is brief. Okay. I'm out of time. All right, I guess this has to be another video, like a third video. So I'll see you guys next time. All right, that's it for now. And then we'll talk about time complexity at the end of everything, once we look through these various optimizations. Ciao.